Welcome back. This is our last lesson of Unit 8. We did it. Um, so to finish off our combined functions, we're going to talk about modeling with combined functions. And I will say that of all the things we do in high school, this is probably the closest lesson to real-world application of modeling in mathematics that I can think of. So without too much further ado, let's take a look at some questions. I'm going to point out we're actually going to look at two questions today. I know it doesn't sound like a lot, but two in this topic can be quite a bit, especially when you're doing complex modeling. The first one is based on data collected, and this is actually fairly realistic data, and it's the kind of thing that you would do. The other one we're going to try and put together by situation. The first one here, though, we are actually just given a table of values, and these may or may not have been generated from an actual mathematical equation, but they could have been generated from a real world experience as well. So in this particular question, we're looking at the height versus time data of a bungee jumper. And we want to know basically, can we model where the bungee jumper will be at any given moment, what their height will be as a function of time. So I originally had just put down here that you could plug all that data into Desmos as ordered pairs, but that seemed really cruel and unusual. So you'll notice that I have actually under part A where it says to enter the points into Desmos, typed them out as a whole. So you're more than welcome to copy and paste from your notes document if you actually want to try this and work along with me. If not, I guess it doesn't really matter how long it takes you to plug in things if you're not actually doing them. So anyway, let's go over to Desmos and see what happens. Oh, that's me, not Desmos. Let's try Desmos. Okay, that's better. Desmos is much better looking than I am, so something much more worth looking at. Anyway, I've copied all the points that I have to plug in here. Oh, that's not what I want. Let me try that again. Cooperate with me. Okay, let's plug those points in. That was a lot faster than typing them one at a time, and none of them are visible, but that's because they're all bigger numbers. So they look like that. Okay, so when I look at that, yeah, I don't know, linear, quadratic, what kind of function does that look like to you? I think part of the problem is our scale is a little bit messed up. So I'm going to do this to get the y scale right because it looks like I've got all my y values in. But I'm going to adjust my x, and it looks like most of my x values, well, all my x values are between 0 and around 40. So I'm maybe going to go from x equals -5. Let's make it -10 just to leave a little extra padding room there. And we'll go up to x equals 50. Oh, okay. That actually is looking much nicer. I'm just going to see if there's a nicer scale I can put on there. Yeah, that looks good. Okay. So now I think that looks much, much more like a pattern. How to get that pattern is another story, but at least I see the pattern now. Okay, I want you to just look at that for a moment and just think about what functions come to mind when you first do this. Now there's two that come to mind fairly quickly with me. One of them, I hope you notice, is a trig function. And because it looks like it starts off at a high point, I'm going to actually try to model it with cos. And I'm going to use f at x equals cos x. Okay, obviously not hitting that one too close. We got a couple problems here. First of all, the amplitude's not nearly big enough. We need an amplitude of about 100. Okay, so now at least we're starting off at the right spot up here at 0, 100. But I can also see that the period is off. So we have a peak at 100. We have another peak, a peak of 100 at 0. We have another peak, even though it's lower, over here at 17 or 18, somewhere in there. and another one over here at 35 or 36. So what that's going to suggest to me, why are they putting them backwards? At least now it's 35 on the left and 36 on the right. That suggests to me that the period here is about 18, maybe 17 or 18, but around that. So I'm going to try putting in a period, a period of 18. And the way that I do that, I'm working in radians, so it's just going to be 2 pi divided by my required period, and I think it's supposed to be 18. So when I do that, does that look better? And I'd say that's actually pretty good. It doesn't deal with the fact that these peaks keep getting smaller and smaller and smaller, but it looks like we've at least got the maximums and the minimums in the right places. Period looks good. I think everything else looks pretty good too. Just move it up a little wee bit there. Okay, so that's not a bad model to do the up and down part. Now we have to deal with the fact that it's dropping off over time. I'm trying to think of what function does that. And the first thing that comes to mind, I'm just going to turn that one off for a second, is going to be an exponential function, specifically an exponential function with a base less than 1, so it drops off as time goes on. So I'm going to start off with y equals, what base should we try? 1/2? One half to the exponent x. Oh, that dropped off way too quickly. Also, it started in the wrong place. It started at 1. We want it to start at 100. And I can fix that by putting a 100 coefficient in front. Okay, so it started in the wrong place, but it dropped off way too quick. We want it to go through this peak, and then this peak, and then this peak over here. And it drops off almost immediately. Well, what that tells me is that maybe the fraction's not a half. Maybe it's a little bigger than a half. I'm going to stop working in fractions, by the way, because it's a little easier here. So 0.75, still too small. Let's try 0.9. And by the way, at this point, I could try to do mathematically, like a mathematical analysis of this, but for the number of trial and errors I'm going to do, you know what, I'm just going to try it in Desmos. Still a little too little. Now we're getting closer. 0.97. Okay, now we're a little too big. 0.96. And by the way, we could keep going here as long as we want until we get the accuracy we're looking for. 8, 9, 6, 5. Okay, actually that's looking pretty good. That looks like it's pretty much going through those peak points. Okay, so now we have one curve that kind of gives us the ups and downs, one curve that gives us the fact that it's dropping off over time. So let's see what happens if we put those together. I'm going to turn that off for a second. Oops. Turn those off for a second for the great reveal. And I think if I just multiply those together, life should be good. That's a little bit of a lie. We're going to have to do a little modification. Y equals f times g. And when I do that, the first thing I notice is it's like super, super tall. Okay, that doesn't mean we messed up. It just means we're leaving out one little detail that's kind of important here. And that one little detail is that I gave it a coefficient of 100 in f at x, and I gave it a coefficient of 100 in g at x. And actually, it only needs a coefficient of 101. So what I'm going to do is actually, I could take this answer, divide it by 100, or I'm just going to remove the 100 from one of these. And now we have that purple graph. So let me turn these two off for a second, the individual pieces. That's the purple graph, and then I'm going to throw the points back on and see what happens. And yeah, they're looking pretty good. Okay, so I think we just came up with a pretty decent model for this set of data. And it's f at x times g at x, which is just another way of saying, let me do one more function on here so I can just do it as one. It's going to be that f at x times that g at x. And there's our final model to represent this bit of data. So just to recap what exactly we did, we basically looked at it and said, okay, I see a bit of a trig function there, and then I tried to do the trig part of it. And then I saw that there was a little bit of a drop off, and that drop off literally, it could have been linear, it could have been quadratic, and we may have been able to actually model it that way. We could always try doing that way if we wanted to. I don't, because I want to keep this lesson a little bit shorter, but if you wanted to try it, you could. And you might get a half decent model because at least for the part of the data we're getting here, let me just try something really super quick. I did negative 0.8.5. Oh, wait, not a decimal, bigger than 1.5, 1.6, 1.7, 1.8, 1.9, negative, oh, 1.9, negative 2.2. Okay, so that would actually kind of model the drop off as well, but it misses here. It's a little too low, and here it's a little too high, or vice versa, depending on which one you're talking about. So linear doesn't exactly cut it. Could quadratic? Maybe. We're not going to worry about it. We've come up with our model, and it's pretty impressive. So let's go back and fill that in our sheet. So there was the model as we figured it out in Desmos, and we can see that there's definitely a trig part and definitely an exponential part. So combining functions is actually super powerful as long as we can combine whichever ones we want. And we can. We know a whole bunch and we can combine them all. And then we can solve problems like C. At what time is the bungee jumper finally, what time will the bungee jumper finally stay within 5 meters of the rest position? By the way, this must be a very high bungee jump for it to, well, starting off at 100 meters, that's like really, really high, but that's way higher than any real bungee thing, I think. Actually, I don't know that much about bungee. Maybe it isn't. But when will they stay within 5 meters? So mathematically, this would be tricky to solve, but we have a tool. We have Desmos. So what I'm going to do is just say, okay, if they're within 5 meters of the rest position, which on our graph is 5 meters of zero height. And by the way, I should point out zero height here is not height above the ground, or sorry, is not the ground itself. The ground is actually way lower. This is just the rest position. So basically where they're going to be when the bungee stops bungeeing, if that's a word. When they're just hanging there in midair, they'll hang at height 0. So we want to see when they're going to be within 5 meters above and 5 meters below. Oh, below. There we are. Okay, so I just keep looking over here and find out when will the bungee jumper stay within the 5 meter range. Okay, so here they definitely go a little below the -5, and here they are just within the 5 meter range, 4.68 meters. And it looks like after that they're going to stay in there. So the last moment they go beyond is this one right here. This is the last time that they'll be more than 5 meters away from the rest position. So the answer to that question is going to be 82.664 seconds, which sounds maybe a little bit too detailed. I'm just going to say about 83 seconds. There we are. About 83 seconds. Why can I not write today? Oh yeah, because I can't write any day. There we go. So at about 83 seconds, the bungee jumper will stay within the 5 meter range. And then at some point, and this is where modeling often screws up, is if you go far enough away, this suggests that they're going to bounce for a long, long time. Although even this says at 3 minutes, they're only going to be, what are we here? About 0.2 meters. So 20 centimeters within it. So they're just kind of like slightly vibrating in midair. Okay. Okay, so there was a good modeling of some real world behavior. Now let's try something slightly different. Or, yeah, let's go to the next question. A skier is skiing down a hill through a series of moguls. For those who don't know, I put a picture there. A mogul's like these little bump hills so that they're kind of like going bump, 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 bump all the way down. I know that you can't see what I'm actually doing with my hands, but they're going bump, 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 bump all the way down. The hill is 100 meters high and has a horizontal length of 200 meters. That's pretty steep. The moguls measure about 1.5 meters from crest to trough, so that means from the top of the mogul to the bottom of the mogul, if they were on flat ground, they'd be about 1.5 meters. And they're about 5 meters apart. So as you're going down the hill, you hit one mogul and then you'll hit the next mogul 5 meters later, roughly. Assume that the top of the hill is at the mogul's rest position. So you're starting not within a crest or a trough when you first begin this. And we want to see if we can develop an algebraic and graphic model to show the height of the hill versus the vertical distance. Okay, so let's go back over to Desmos and see if we can first of all figure out what this is even really asking us to do. So I'm going to get rid of a whole bunch of these equations that we don't need anymore. And I am going to point out that the hill, not that this is super important, but we want our hill at the height to be 100 meters high. So that's going to be 0 horizontal distance, 100 meters high. And we know that it's going to be 200 meters horizontally. So at 200 meters, it'll be down to 0. So basically, we need to go through those 2 points. And kind of like we did last time, let's see if we can at least make our scale half decent. So I think it's good side to side, and the bottom looks okay, but I only want the top to go up to maybe about 110. So let me make that modification. Okay. So y goes from, we should make that a little smaller. I'll make it -10 to about 110. And again, you'll notice I always go a little bit over just to kind of make it so that you can see the end points on the graph instead of being like right on the edges. Let's go up by, I don't know, is 20s okay? Doesn't want to do 20s. 50s will have to do, I suppose. Oh, wait. Sorry, that's the y-axis. We want to go up by 10s. And we want to go up by 20s on the x-axis. Yeah, that looks decent. Okay, so now we need a hill that goes through 0.0 or 0, 100 and 200, 0. So that's going to be y equals mx plus b something x plus 100. And we can try -1, -1, and that's obviously too steep, so we'll try -1/2, which makes complete sense because it's a drop of 100 over a run of 2. Down 100 over 200 is -0.5. Okay, sorry, I was so much into like just changing numbers to meet the data, I didn't think about the obvious way of calculating a slope. Okay, so that's what it looks like. That's that part. Now the next part, I'm going to turn that off for a minute, and I'm going to move this up just momentarily. The second part here is I've got hills that go up and down and up and down and up and down. So I'm going to model that with a trig function, and I've got my choice. I can use cos or sine, and technically I could use either of them and modify it into the other. But we're starting off at a rest position and then going up from there. Actually, I guess the question says we're starting at a rest position, but it doesn't say we're going up. I'll assume we're going up. And that means I think it's probably best to model this with a sine function. And I am going to zoom in on this because I want it to be a little bit more clear. And we can zoom out and the ratio, the scales should be fine. So not a big deal. Okay, so now we want the few more criteria we had. We wanted the bumps to go up and down, well, total of 1.5 meters between the top and the bottom, which means they have to have an amplitude of half of that, or 0.75. Okay. And then I think the last thing we had to take into account is that they're 5 meters apart, which means the distance from here to here should be 5 meters. It's not, it's 2 pi. So we can fix that by changing our period. Instead of just the x, we put 2 pi over x. Sorry, 2 pi over 5. And yep, that gives us our crests and troughs 5 apart each. This goes from 1.25 to 6.25. That goes from 3.75 to, should be 8.75. And yeah, it all works. Okay, so we've modeled the actual mogul part. Now all we have to do is put these together and see what our hill's going to look like. And there we're back to roughly where we were before we zoomed in. And one thing I did kind of didn't goof on, but I'm going to fix. Instead of calling these both y, I'm going to call the hill, what should we call these things? Let me just call that one the slope at x. I don't know. Sure. I don't want to call it h at x because I'm actually going to use that for my final answer. And these ones will be the mogul at x being the horizontal distance. And then to put those together to figure out what my hill's going to look like, the height at x should just equal the slope at x plus the moguls at x. And I'm going to turn those two off for a second. And yeah, that's actually kind of more or less what the hill looks like. So overall you're going down, but there's a bunch of little downs and ups, and each one of those downs and ups is a mogul. So just to zoom in to see what it looks like a little bit more. That's actually what the skier is more or less experiencing. Slight ups and bigger downs all the way down the hill. Of course, in real life, moguls aren't placed this beautifully and precisely, but from the information we were given, I'd say that's a pretty good model. Ooh, okay, my computer just freaked out there, so there may be a little glitchiness there, but I don't think we lost anything. It's just, yeah, there's our model. So again, I could also write h at x if I wanted to actually use one notation instead of a composition of things. It's equal to that plus that. I think you can see that it's going to be the same whether I do it with the actually just adding the two functions s and m, or, oop, that sounded wrong. Whether I add those two functions or I just go to the h at x as one single function. You can never pick variables that aren't going to screw up somehow. Anyway, that's the equation that we actually get. Okay, so our mathematical model, or algebraic model, looked like h at x equals negative 0.5x plus 100 plus 0.75 sine 2 pi over 5x. And the order of those terms doesn't really matter. I would say normally we would put the plus 100 at the end. That's normally where you put translations or constants, but other than that, I think we're good. As far as the graphic model was the picture that we just had. I'm not going to redraw it here, but we have it in Desmos. All right, so that is it for the day, except for one question. This is the first time I'm giving you just one homework question. And if it's one question, you better anticipate that it's going to be a doozy. So for this one, I've actually made a note there. I would like you to take a screenshot and share it, or be able to share it with the class. There is no right answer to this problem. There is no one model function that you're going to find that's going to work. Question 10 is going to give you a set of data, and in fact, I have put it at the bottom there so that you can cut and paste it into Desmos without having to type it all. I don't even remember what the context for the question is, but you're going to want to try and find a model doing anything you can with any of the functions we've learned. There are several drastically different models that I have seen students submit that are all just as close as mine is, and mine's not even perfect, and it's rather complex. So this is not a right or wrong type of question. This is I want you to try. I want you to see. I want you to go through the frustration and the realization of how these work. And I know that sounds kind of cruel, but that's the best way you can do it. And it becomes just a challenge after about 2 minutes to try and get something really cooler. So this seems like a good time as any to go over and do a quick review of what all functions you know about. They're all listed there. We have our linear functions, our polynomial functions, which were broken down into a whole bunch of different types, quadratics, cubics, quartics, quintics, etc. We have our reciprocal functions, and even within that, we've got some pretty drastically different looking ones, depending on whether the bottom is never equal to 0, or the bottom is sometimes equal to 0, or equal to 0 at multiple places. We have our trig functions. We have sines, coses, tangents. We have all of the secondary ones that you can do, which are just reciprocals of the first ones. We have our exponential functions, both exponential growth and decay. We have our log functions. We have radical functions, not that we really covered them in this course too much or went back over them much, but we do have our radical functions from grade 11. Those are the square roots and the cube root functions. And then we've got what we've learned this unit, which is putting them all together by adding, subtracting, multiplying, dividing, or frankly, doing anything else that you want with them. So given all of those options, I would like you to spend maybe 10, maybe 15 minutes to try and do the best model you can. If it's not close, or if it's not close in certain spots, that's okay. I'm not going to be upset. I'm not marking it. But I do want to see how close people can get. And when we're in class, I can share my model, and if anyone else would care to share theirs, that would be awesome. So I'm going to leave you to do that. Normally I would ask you if you have any questions or tell you if you have questions to contact me. This one, don't. Don't even bother. Don't ask me for help. Try it on your own, see what happens. If you don't get it, you don't get it, but try something.